Okay, so yesterday we discussed several things, one of which was the cosmological constant problem, right? So we discussed that, we showed that observations from type 1a supernovae combined with baryon acoustic oscillations and the CMB all favored that the universe should be accelerating, right? And we examined some models of cosmic acceleration, right? The simplest, of course, being the cosmological constant, right? Which was suggested by Einstein way back in 1970, right? We also realized that the cosmological constant had a very interesting basis in physics, right? That it turned out to be associated with the vacuum energy, right? But the problem here was that the vacuum energy could be very, very large, right? Whereas what we see today is extremely small, right? And there's no real satisfactory explanation for this currently, right? For the really small value of dark energy, which we see, which is roughly rho dark energy, is roughly 10 to the power minus 47 GeV4. So it's really tiny in terms of particle physics units, which are typically much larger. So we also, I just started talking about the initial conditions problem. So if lambda actually arises, as some kind of condensate from inflation, as we believe dark matter and radiation and baryons did, then we have some issues with its value, which is really tiny compared to that of matter or radiation at early times. And I also discussed in this context the concept of trackers. And trackers had this very nice property. Here's a simple example of a tracker that, the energy in the tracker could scale like radiation or matter and then dominate today, right? And so I had discussed some simple models of trackers, right? So one of them, so typically, your V of phi, in some trackers it goes like this, right? Like phi to the power minus p, right? And in other trackers, it goes something like this, which is the V is equal to the cos lambda phi. Now in this case, the exponential value of this is e to the power minus lambda phi. So this quantity behaves like a tracker out here and then oscillates. Whereas here, a simple example of this is a coth to the power p phi, which behaves like this on the tracker wing and then approaches a lambda-like distribution at late times. So these were examples of some models which might lead to dark energy from a large class of initial conditions, right? Because, the class of initial conditions will be quite large. I'll skip this now. Right. So all of the models I discussed yesterday had this formulation, which is also the formulation used for inflation, right? And it's directly related to the Lagrangian for a point particle in classical mechanics, right? So again, go back to Landau-Lifshitz, volume 1, mechanics, and you got the classical Lagrangian for a point particle. The potential energy becomes V of phi, kinetic energy it becomes half phi dot square. But this is not the only way to construct Lagrangian for dark energy. All right. Just have a little bit of water. Another way of doing this is to commence not from the Newtonian non-relativistic point particle Lagrangian, but from the relativistic particle Lagrangian, which, as many of you may recall, has this form. And now if I do the same transformation from, phi going to r, I get this very simple Lagrangian. It's called the Born-in-field Lagrangian. It comes in tachyonic models, string theory, it arises. And this has played a very important role in dark energy model building in the following manner. So let's start with this Lagrangian. And, you should believe me when I say that the pressure here, when I vary this Lagrangian, right, I get this term for the pressure. Again, it turns out to be negative, right? But it has a different form from the other Lagrangians we discussed. It's inversely proportional to 1 over rho being the density, right? And A here is nothing but V naught squared, right? So what happens is that if you want to put this into your conservation equation, which is nothing but dE minus P dV, you'll remember this from thermodynamics, right? It's valid here as well. You put this in here, it's a little exercise to give you rho as a function of A, and rho is a square root A plus B times B divided by A to the power 6. B is just a constant of integration. So now you see a remarkable thing, that when A is small, that means in the early universe, right, this term dominates, and the density in this thing called the Shaplegian gas goes like 1 over A cube at early times, just like matter, right? Just like matter. At late times, however, you can neglect this term and rho becomes constant, just like the cosmological constant, right? So this was a very, very beautiful property of the Shaplegian gas, right? Discovered by this set of people way back in 2001. And immediately people thought, well, look, since the Shaplegian gas behaves like pressureless matter at early times and like the cosmological constant at late times, maybe you can unify dark matter and dark energy, right? Because, perhaps nature should be economical. And, why not have just one description for the two? People are still looking for that. Unfortunately, Shaplegian gas does not work. When you analyze perturbations in this model, it behaves differently from what you would like dark matter to behave. But nevertheless, it's played a very important role in our understanding of dark energy. Another thing that the Shaplegian gas, one realizes when one studies this model, is that two very different Lagrangians can give rise to the same equation of state, right? This is quite interesting. So this is the Shaplegian gas Lagrangian in this form, Born-Infield form, right? And I can also write it in this form, the canonical form, but put in this form for the scalar field potential. And in both cases, I will get the same equation of state. So this tells you that on occasions, the equation of state may not be unique, right? It can emerge from two different fundamental theories. So this is also interesting. It's just nice to bear in mind. Whenever you start working in a new discipline, little surprises spring forth, and they kind of help you understand the physics a little better. All right. There's another way of constructing dark energy I didn't speak about, but I'll spend just 2 minutes on this. And it is, suppose you have a scalar field with some kind of a minimum, and the field starts oscillating about the minimum. Well, then if you take the RMS value of the equation of state, if this is the potential, phi to the power 2p, the RMS value of the equation of state is p minus 1 over p plus 1. This is the average, time average rather. That's a better word for it. P minus 1 over p plus 1. So if I put p equal to 1 out here, which is just phi square, m square phi square, I get dark matter. And if I put p less than 1/2, it corresponds to dark energy. So this is a very beautiful result. This is really like a virial theorem, right? It's a virial theorem for the scalar field. It's oscillating very rapidly. And so this potential can give rise both to dark matter and to dark energy, depending on how the potential is curved. And in fact, this form has been used to construct models of inflation called monodromy inflation. Now, if you use this potential blindly for dark energy, it won't work. For the simple reason that you will run into a severe fine-tuning problem. Because, it's not like inflation, right? When the field starts rolling down the flat potential, it gets heavily damped, it gets stuck in one place, right? And you have a fine-tuning problem. But you can get around that if, again, you appeal to hyperbolic potentials. So this one, for instance, right, it has exactly an exponential behavior at early times. So it behaves like a tracker. And at late times, it behaves just like you want it to. So this potential can describe dark energy, coming from a tracker behavior, or it can describe dark matter. Here I've just shown dark energy, but you can describe dark matter. And it has this beautiful property of having a large initial basin of attraction. So this potential can describe both dark matter and dark energy, and it has been heavily used in recent years. Many people have used it for both dark energy and for dark matter. It was first discovered by myself and Lim and Wang way back, almost 20 years back. All right, so let's move on to something really strange and really weird, right? And that is phantom dark energy, right? So phantom dark energy was suggested back, about Bob Caldwell in 2002, and he looked at the data, the supernova data, very carefully, and he said, wait a minute, if you really want to, plot your theory versus observation, what you really need is W should be less than -1. I mean, even a cosmological constant doesn't fit all that well, right? And he was correct for the initial data set. And so he suggested this to be phantom dark energy. And I'll tell you in a minute why he chose this word. So dark energy requires the violation of the strong energy condition, right? This is also true for inflation, right? Now you are familiar with this, right? Whereas phantom dark energy requires a violation of the weak energy condition. That is, rho plus P now should be greater than or equal to 0. You need to violate it. So from here you get that W should be less than -1. But phantom models, okay, so here is where he got it from. How many of you have seen this movie, Phantom Menace? Yeah, good. So I think it was just released around the time he was thinking about it, and so he called it this one. The Phantom Menace, Cosmological Consequences of Dark Energy with a Super Negative Equation of State. Just a year or so later, a couple of years later, people wrote a paper called The Phantom Menace, right? Constraints on Low Energy Effective Coasts, because they realized immediately that the simple models of this phantom dark energy, ran into serious troubles, serious instabilities, coasts, whatever. So people forgot about these. One simple example of a problem is that, if you evolve, so what happens here is that you got rho dark energy, and it's going like a to the power -3 into 1 plus W. So usually this quantity is positive, so it's declining with time. And if 1 plus W is 0, then it's cosmological constant. But if this quantity is less than 0, right, then you have effectively this times, and I should remove this and put a modulus sign here. So this thing is growing. Right? This thing is actually growing with time, with time, right? That's the thing with phantom, right? It actually grows, and at some point of time, the densities in phantom and in matter will equalize, and soon after that, the Hubble parameter goes to infinity, which is quite clear from here, right? If the density grows. So this is called a big rip singularity because everything gets ripped apart, right? The galaxies, everything. Nobody really believes this will happen. And very soon after this was discovered, in fact, in the same year, I think, it was found that actually you can get a phantom-like equation of state from modified gravity theories, right? Where this is not the pure equation of state, this is an effective equation of state. And these theories are very well behaved. They have no singularities, no ghosts, nothing. And they find support in BAO observations. So this is also very interesting. So now let's come to a different subclass of models. So far, I've been telling you that you can get cosmic acceleration by modifying the right-hand side of the Einstein equations. Basically adding something to the matter sector, right? This could be anything you want, Chaplygin gas, phantom, quintessence models, whatever you like. But you can start worrying about the left-hand side, the gravity sector, right, of the theory, right? And in fact, Einstein's original proposal was to bring the cosmological constant into the left-hand side, right? Not much is known. Nowadays, you put it into the right-hand side. And these kind of class of models where you modify the gravity sector leads to geometrical models of dark energy. And examples are, extra-dimensional models, sometimes called brane world models, scalar tensor gravity, right? Brans-Dicke type models, string M theory inspired models, and F of R gravity. Okay, and several of these models have played an important role in constructing inflation, right? So I'll talk a little bit about this very important class of models today. Now, let's come to the very first inflationary model. Curiously, the very first inflationary model, the one discussed by Starobinsky in 1980, did not involve scalar fields at all, right? Okay. What Alexeyev did was, he realized that when you take quantum corrections into account, right, the classical Einstein-Hilbert action develops an additional term which is proportional to R square, right? And this term is very interesting, right? Okay, its importance increases at higher energies when r is large. And this term leads to a box r term in the equation of motion, and therefore to fourth order gravity, right? So you know that Einstein's theory is second order gravity, right? In the sense that you don't have equations beyond a double dot, right? So a double dot is minus 4 pi g by 3, and sum over rho plus 3p, right? So second order theory, right? Also you've got an equation for a dot, right? But here you have fourth order equations, right? So making it more interesting to analyze. But if you are worried about fourth order equations, fine, that's fine. There is a very nice transformation. You can bring this action to the Einstein frame, and you get this sign of, you can associate it with a scalar field in a different frame with this potential, and this potential, this is a slow roll wing, allowing inflation to commence. Okay. So now the important point here is that this is a very successful model of inflation, which arises solely by modifying the gravity sector of the theory. And this model is in very good agreement with observations, R square inflation. You must have seen this picture, right? Yeah. So I'm just repeating what you already know. Good. Very good. Now, why I mention this is that, people took some inspiration from this model, and when they started doing dark energy model reconstruction, people said, well, if this gives rise to early acceleration when r is large, perhaps the inverse of this will give rise to acceleration when r is very small, right? And indeed, this turned out to be true. This turned out to be the case. But once more, when people analyze this model a little more carefully, they realized that it developed very strong instabilities and also did not pass solar system tests. So, it's possible to modify your gravitational Lagrangian so that the universe accelerates, but then you've got to study the weak field limit, like the solar system, and see whether you actually get, the sensible parameters for the planets. And if it does not, doesn't pass solar system tests, the theory is done for, right? And this is what happened to this class of theories. But they inspired deeper thinking, right? Okay? A failed theory is not necessarily a bad thing, because, you go deeper into it, see why it failed. And sooner and later, pretty soon, people realize that, well, you can develop Lagrangians which have late time acceleration, provided the second derivative is positive, right? And here is an example of a very simple polynomial Lagrangian, right? Hu and Sawicki. And, it gives rise to very sensible late time acceleration without the need of any dark energy. So you don't put in any dark energy field, you just modify your Lagrangian with this f of r term. And there were several other papers that came, almost at the same time as this one. Can we have the questions at the end? Because I'm just running a little short of time, right? You saw how, long it took, right? But keep your question, I'll definitely answer it. So now, this is one way of doing this. And this is not the only way, right? People have worried about dark matter also, right? So this is another big unknown, right? And people have worried whether you can also modify the laws of gravity to explain dark matter, right? Because dark matter is another unknown. You all know about dark matter, right? Yeah? Everybody, or no, somebody does not know, right? Nobody's nodding, right? Nobody knows, right? Or everybody is a little sleepy after that food, right? Don't eat too much before my talk. Huh? Okay, so basically, suppose, this is your matter concentration, right? All right, and you are sitting somewhere here. You apply Kepler's laws, right? MM cancels, V is square root GM over R, right? And the minute, so you can take this to be the sun, right? So, the minute you go out of the sun out here, M remains constant, the solar mass, and V goes like 1 over square root R. This is how Kepler discovered his laws anyway, right? But now you try applying it to the galaxy, right? And you find, wait a minute, something strange is happening, right? As you move out of the galaxy, right, the velocity is not decreasing. The velocity is a constant, right? And if you plug this back in here, you find that the mass should be growing with radius, right? Way beyond the galaxy. So this is a visible galaxy, and this is a dark matter halo, right? Okay. And so this is one of the main observational evidences is now we have almost 1,000, these are known as rotation curves. You have almost 1,000 rotation curves for galaxies, right? And we are doing this in Pune also. My neighbors in NCRA are doing this very well, right? And you find almost every galaxy has a very strong dark matter halo, and especially the dwarf spheroidals, they're enormous dark matter halos, right, around them. So a clever person Milgram, 1983, he suggested that, look, perhaps you don't need dark matter at all, right? Suppose you are willing to give up on Newtonian gravity either on large scales or in regions experiencing very low acceleration, right? So Milgram said this, let's focus on regions experiencing a very low acceleration, right? Because that's where the dark matter takes over. So I'm just going back to my derivation, right? So you've got now two accelerations, right? You have this force law, F is equal to ma, an is Newtonian, right? G is your, and you equate the two, right? An is G, right? And G is just gm over r square, and this gives you, and then you equate this to the centripetal acceleration, right? AC is an, equate these, and you get this, right? Okay. Now, Milgram said, okay, let's introduce modified Newtonian dynamics, which means that F is not equal to ma, right? So what is F? In regions where the acceleration falls below 10 to the power minus 8 centimeters per second square, right? The acceleration law becomes F equal to ma squared by a naught, right? In high density regions, it still remains the same, right? Now what happens here is very interesting, that your acceleration squared is, again, your m cancels, right? Is a naught times g. So a is square root a naught times g. Now you plug in g from here, right? Gm over r square, and equate this quantity to the centripetal acceleration. So v squared by r is a. So it's this quantity, and now this r cancels with this, and the velocity is a constant, right? So you get your flat rotation curve when a drops below a naught, right? Okay. So this is an example of modifying an equation of motion without introducing a dark matter into it, right? Okay. And this is very simple also, right? Of course, the acceleration has to be really low. Acceleration was 980 centimeters per second square. You can imagine what a tiny acceleration this is. But this is the acceleration in the outer regions of the galaxy. Of course, you can ask, well, one should be able to differentiate. Can one differentiate? Can one think of a test which will differentiate dark matter from MOND, right? And very soon, a test came to us as if, right, like, you know, somebody gave us this big present, right? And this big present was the bullet cluster. And they found an extremely rare event of two clusters colliding. Now, clusters are very rare objects in the universe, right? The density of galaxy clusters, right, is very, very low, right? You know, and here you had these two objects colliding, and, you know, when you do a kind of multicolor observation, right, in different wavelengths, you know, X-rays, putting everything optical X-rays, right, and also weak lensing, you get this interesting map. So what you see here, so I'll just read it out, right? Due to a collision which occurred about 100 million years ago, the two clusters of galaxies participating in this merger have moved ahead of their respective plasma clouds. These are plasma clouds. So this is a bullet, right? You know, you can see the ram pressure, right? You can see the shock wave, right? So these things have moved like this. But the remarkable thing was not that. The remarkable thing was that when they did a weak lensing analysis here, they found that the center of mass is over here and over here. So it's as if the mass associated with these clusters does not feel the baryon, the immensely hot and, you know, pressure of the baryons, right? It's just invisible. It just moves ahead, right? Okay. So this led to the conjecture that the primary mass component, therefore, is likely to be dark and non-baryonic, non-interacting. And in fact, the title of this paper, right, was a direct empirical proof of the existence of dark matter, right? So this is very interesting. I mean, the debate has gone on, right? You know, so because if it was MOND, then you would expect, I mean, I would expect, at least naively, that, you know, you would have, you know, things associated with where the baryonic mass was, but here you don't, right? So this is just a way of, you know, how science progresses, right? You have two hypotheses explaining the same phenomenon, and you're going to find some test that can differentiate them. In this case, a nice test is there. So now we have return to dark energy, right? And so you have this nice way of, you know, trying to explain dark energy either by modifying the Einstein-Hilbert action in this way, like the Starobinsky did, right, for inflation, or there is yet another way of doing this. And I'm going to turn to that next. And that way is by means of extra dimensions. Now, the idea behind extra dimensions is very cute, right? And it arose with the seminal work of Kaluza and Klein, who actually compactified the fifth dimension. So here's the fifth dimension. They rolled it into a tiny cylinder, right? And when you do that, and you write the Einstein-Hilbert action in 5D, it actually decomposes into the 4D action, which gives you GR, plus a term which gives you electromagnetism. And another scalar field, sometimes called dilaton or radion because of the radial compact dimension. And this was very thrilling because people felt that maybe you can, just no need to introduce electromagnetism, right? That's also a field, right? Maybe you'll just get it out of a compact fifth dimension. Right? That's beautiful. There's been a whole tendency here, right? A kind of a school of thought that says, well, going back to Einstein almost, that let's try and recover the physical fields from geometry. There has been the opposite also. Let's try and recover the geometry from the physical fields, right? So people have played both games, right? But this is an example of a very beautiful example. And indeed, this was extended to include standard model fields in the 60s and in the 70s, right? When people started working with more complex, this is the U1 gauge symmetry, when people started looking at SU5 and, more complex symmetries, right? They worked in this, extended this formalism. But more recently, there has been another advance, right? And that is the concept of the brane world, right? And in this case, you don't have a compact extra dimension, but the extra dimension can be infinite, right? And in this case, our universe is then like a membrane suspended in the fifth dimension, right? So how many of you have seen this movie where the chap moves through the fifth dimension? What is it called? Interstellar. You've seen that, right? The wormhole, right? And he says, hey, we are going through the bulk, right? So the idea is taken from here, right? This is known as the bulk, right? The fifth dimension, right? And of course, you can construct wormholes also from going from here to there. I'm not going to do that, right? But people have played with that also, right? So the idea here is that you have the brain, right? And the standard model fields are trapped onto the brain. Otherwise, I would be able to just jump up and go into the fifth dimension, right? Not come back, right? But in fact, particle accelerators are probing this, right? Whether strong and energetic enough interaction can lead to some loss of energy, right? The extra dimension. Gravitons, however, can escape into the bulk. So now this kind of a theory, depending on the action, right, can change your expansion law either at early times or at late times. Early times sometimes you call a UV modification, late times sometimes an infrared modification. So I'll talk about both of them a little bit, right? Because both have very, very interesting possibilities, right? So let me introduce the Randall-Sundram model, right? In this case, what they did away with the fourth dimensional action, right? So there's no four-dimensional action, there's a five-dimensional action, right? So M is the Planck mass in the fifth dimension. If you like, is the gravitational constant in the fifth dimension, right? And they have a tension on the brain. So this is the brain tension, right? And when you write the Einstein equations, you find that your usual 8 pi g by 3 rho is now influenced by an even stronger term proportional to rho square, right? So in fact, when rho becomes much larger than rho square, a very interesting thing happens. H goes up. And when H goes up, your equation for the inflaton experiences a lot of damping. So, this is the inflaton equation, right? But this should remind you of a very familiar equation, the equation of a damped harmonic oscillator, right? Okay. And so you want slow roll. How can you get slow roll? Either by making V prime flat, making V prime small, right? Or by introducing a lot of damping, right? So this does just that. The fifth dimension does that, it increases H, right? As a result, you can get inflation even from a very steep wing, which originally was associated with a tracker, right, in dark energy, right? So this is a really big discovery, right? Okay. And this allowed one to actually try and unify inflation with dark energy. As I mentioned earlier, they both have strongly negative equations of state, so it could be they are both part of the same thing. And this idea called quintessential inflation was first talked about by Peebles and Evelinkin, not in this context, and later by some of us. First, of course, by Ed Copeland, Andrew Liddell, and others, and soon after by us, in the context of the Randall-Sundram model. So this is an interesting model, right? But it's not doing anything for dark energy. But this model may help explain. So this is your, picture, cartoon of the universe, the inflation, deceleration, acceleration, right? So maybe the two are unified. Why should the universe accelerate twice? Okay. This is one part. The other thing I wanted to just briefly mention, that what happens if the extra dimension is not space-like, right? But is time-like, right? So you have another dimension of time. In this case, this plus becomes a minus. You get a dual to this equation. And this can lead to singularity avoidance at early times. And that is very easy to see. So how do you get a singularity, right? In GR, h square is proportional to rho. As rho goes up, h goes to infinity, right? This is classical singularity. Okay? But if you replace this equation with this equation, right, what happens? You can't increase rho beyond rho c, right? When rho is equal to rho c, this term becomes 0. So h becomes 0, right? And so at this point, you have a big bounce. So you're replacing this point with a bounce. And it's quite remarkable and very interesting that this exact equation arises from two completely different theories. One is a theory with a time-like extra dimension, and the other is a quantum gravity theory, suggested by Abhay Ashtekar and others, called loop quantum cosmology. They give the same bounce behavior, right? So in both cases, the universe bounces, right? And you can ask what happens further, and maybe what happens is something like, the universe goes on increasing, right? From kind of small, you don't know from where, right? You don't know what happened here. So increasing cycles of the universe, right? Cyclic cosmology, essentially. Model of cyclic cosmology. But let me come back to dark energy. This was just an aside. So as I said, you've got this picture of the brain, right? And it can do very strange things, right? You can have singularity avoidance, right? You can maybe join inflation with dark energy, right? But you can do one more thing, right? Now, it depends on your choice of the action. So way back in 2000, almost 20 years back, these three people, Dwali, Gavadadze, and Porati, introduced what has become famous as the DGP model. So what they did was, they took the 5-dimensional action, but also added the 4-dimensional action to it. And when you do that, you discover a new length scale. And this length scale is the ratio of the 4-dimensional Planck mass to the 5-dimensional Planck mass, or the 4-dimensional gravitational constant to the 5-dimensional gravitational constant, right? L is m squared over m cubed, right? And you realize that, you know that the 5-dimensional Planck mass is 10 to the power 9, 4-dimensional Planck mass is 10 to the power 19 GeV. Well, if the 5-dimensional one is about 100 MeV, the length scale turns out to be the size of the universe, right? Okay. So you're getting a large length scale from two large masses, right? And so when you try to study the Hubble parameter, you have this very simple behavior, right? There's no dark energy, and yet you have a constant here, right? You just compare this with lambda CDM. It's very similar. Under the square root it is similar, and here you have one more L here, right? So this new quantity L is playing the role of the cosmological constant. But the expansion is different, right? So there's no need for a tiny lambda, right? Absolutely, there's no small number in this theory, right? You have numbers completely consistent with high energy physics, right? 1 GeV, slightly less, right? So that's it, right? And unfortunately, again, right? Unfortunately, this model has problems with ghosts, right? And other instabilities. This was pointed out in a beautiful paper by Ruth Gregory and others, right? But brain world models without ghosts have been constructed, and they have the distinctive feature that W actually falls below -1. So dark energy is a phantom. And all this work was done very, very, very soon. This was 2000, this is 2002, right? And these models are still alive, right? That's why I'm talking about them today. So what is this model? I mean, you'll agree with me, the idea is lovely, right? You do away with lambda altogether, right? And have a 5th dimension. It's an interesting idea, right? So out here now, it's after lunch and I really don't want to, load you with heavy Lagrangians. So if you want, you need not, it's the same DGP Lagrangian, but all I'm adding is a brain tension. So this is like a combination of Randall-Sundram and DGP, right? In Randall-Sundram, you didn't have this, but you had this and this. And in this case, you have this, and so you have dGp plus the brane tension, and this changes everything, right? So what happens here is that you have lambda CDM, which is this bit, but you also subtract from it some quantity which depends on the matter density, right? And this is, in a sense, you're screening dark energy, because at late times, at early times this grows. So at higher redshifts, the dark energy is almost zero, right? It goes away, and it reappears at late times, right? And this fact that this term is growing with redshift leads to an effective equation of state that is negative. Because what is happening here, it's exactly like this, you see. What is happening here is the following, so this is your phantom behavior, right? That, this is going like a to the power 3 into 1 plus w. So w is negative, so this is growing with time. Dark energy is kind of growing. And you can see that from there, that in this case, your effective dark energy is your lambda minus fz, right? And so this is also growing with time. So this quantity is growing with time. So this property that this is growing with time, there's no funny equation of state here, right? It's just geometry, right? This term is purely geometrical. It's coming from the same L quantity, right? It's the ratio of these two length scales. So a geometrical term is playing the role of phantom dark energy. That's the thing. Okay. So when this happens, you start wondering, okay, what does it do? So again, as I told you, the effective lambda term grows with time, which is this quantity, right? And this tells you that lambda in the past was actually lower than lambda today, right? Dark energy was less, right? And this does not happen in any other model. In tracker models, dark energy goes up in the past, lambda remains the same. Here it decreases. And it's very interesting that this result helps explain a recent measurement of Hubble parameter at redshift of 2.34. And this result, obtained by Delubach et al., is that the Hubble parameter is 222 plus minus 7 kilometers per second per megaparsec, which is significantly lower than what was predicted by lambda CDM, right? So this was some kind of tension with the data, and really our model, this phantom brain model, really passes through it, right? So, and it behaves just like this, right? So it's kind of encouraging that, it does something good for the data, and it will do other things also. This screening mechanism can lead to, what it does really is that it decreases H, right, relative to lambda CDM, right, because of this quantity. And since H is lower, and H enters into the denominator of the luminosity distance, it means that dl goes up, and the luminosity distance going up means the flux goes down, because there's 1 over dl square. So supernovae are even fainter than in lambda CDM, right? So this is a prediction, right? If you have distant supernovae fainter than in lambda CDM, well, that's something in favor of this model, right? The other is that the age of the universe also will go up, right? Because, obviously, so this is H with respect to lambda CDM for different model parameters. There's a substantial dip, right? Depending what you take, right? So a universe containing this kind of dark energy is older than lambda CDM at a given redshift. This is very important because we are seeing very old objects now at redshifts 8, 9, right? And so, the age of the universe will emerge as a very important test of dark energy models, right? That's why I'm emphasizing this. And this will also affect a lot of things. Wherever, in any quantity in which the Hubble parameter enters, that will be a prediction of this model, and other models too. Okay. So then what happens is that there's also a very strange effect that happens. If you calculate the effective equation of state, I'll tell you how this is calculated, right? Because there's no real dark energy here, right? So you make use of a formula that I'll derive tomorrow, right? But if you do this and you plug this into W, then you find that the equation of state has a pole, So it goes, you encountered poles in your maths course, right? So it has a pole at a distinct redshift, right? So this emerges as a smoking gun test of these models. W will not be continuous, it'll have a pole. There's nothing wrong with it because W is not a real equation of state, it's just something that you construct mathematically from the equations. It's an interesting prediction. So the other thing is that when you constrain this model observationally, right, you find some interesting results. That you see this model accommodates lambda CDM, right? Because when you set that f to 0, you recover lambda CDM, and yet when you match it against different data sets, you find that a phantom value is actually preferred, right? In the center of this ellipse is somewhere here. So this is actually preferred. And the other interesting thing is that the larger values of H naught imply a more negative equation of state for dark energy. So if I go towards H naught somewhere here, my W decreases, the ellipse is actually pointing this way, right? And so this kind of a cosmology can reconcile the larger value of H naught obtained from HST observations with CMB observations. Usually you see CMB observations gives a much lower value, right? 68, 69, right? This is a big tension in the standard model. But there is no tension if you look at it in this, within the framework of the phantom brane. So this tells you also that when people talk about tensions between data sets, are these tensions model independent or are they model dependent, right? This tension is clearly model dependent, right? It depends on your a priori chosen dark energy model, because it goes away in this model. All right, I'll end here and I'll take any questions. I'll begin my talk tomorrow on reconstruction methods, which will be completely model independent. So yesterday I spoke about one class of models of dark energy, scalar field models, right? Models in which you change the matter sector of the theory. Today I discussed very briefly models where you change the geometrical part of the theory, right? And both can give rise to acceleration, both at early times and at late times, right? You don't know which model is right yet. But tomorrow I will talk about methods that can be applied just on the data set to derive values irrespective of a given model. That's a reconstruction program. Thank you very much. I'll take any questions. Or you can have tea and I'll be there. You can ask me later. Okay. Okay, let's go to break time then. Thank you.